Yeah. Not really. Just kind of like grouped stuff by sort of topics, like lessons 1 through 10 are what the first test is over.
Good morning, Shat. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Now for the Texas Pledge. Honor the Texas flag. I pledge allegiance to thee, Texas, one state under God, one and indivisible. Now for a moment of silence. Please take attendance now. A message from your healthy shots. Finding strength in numbers does not mean you should set aside the authentic relationships for more friendships. Strength can also come from strong relationships. Have a lovely Thursday, shots.
All right, guys, today we are kind of going into maybe the first stuff that I would really consider new stuff other than like some notation things for linear algebra. And then it'll be our last lesson of the week. Tomorrow we'll do a MATLAB, which means you'll kind of work independently. If you need help on that, I can help you, but otherwise it'll be kind of up to you guys. And then your problem set is due at the end of next week. I want to say Thursday or Friday, but I can't remember which day I put it on. But just keep that in mind. It's over these 3 lessons, kind of like last semester. It'll be kind of every 3 lessons or so you'll have a problem set. So it'll be over these 3, so you have kind of a full week almost to get that done, ask any questions that you might have. Otherwise, we're going to go ahead and start with lesson number 3, which is on elimination. You guys technically have seen elimination before, so there will be some stuff in here that you hopefully recognize, but there will definitely be some kind of linear algebra changes to kind of how we do what we're going to do. So with elimination, you guys have seen this since algebra 1. Oh, sorry, not up there. Oh, that's why it stayed. I was like, oh, it stayed full screen. It never does that. That's the AirPlay that makes it not go full screen. Boom. All right. So elimination you guys saw in algebra 1. And then we've used elimination probably in most classes at least once or twice a year, if not a lot more than that, to solve systems of equations. Like we even did this last semester when we were doing like finding maximums and minimums. And you'd have these equations that you both set the derivatives equal to 0 and you had to solve a system of equations. We learned elimination as one method of solving systems of equations. So in elimination, your goal is, and again, algebra 1, you probably had 2 variables, that you take a multiple of one equation and add it to the other in an attempt to eliminate one of the variables. Then you'd only have one left. You could solve for that one, then plug it back into one of the first 2 and solve there. So like we could take a system of equations like this, and I could look and see, well, I could easily get rid of the y's by adding the 2 equations together. X plus 3x is 4x. Negative 2y plus 2y is 0. And 1 plus 11 is 12. This gives me x equals 3. Then I just go back to one of these original equations and plug that in. So 3 minus 2y equals 1. 2y equals 2. y equals 1. And then there is the solution. Okay, you've also had substitution. We don't really have any. Substitution is not great for more equations. It's good for 2 variables. It's not really that great for lots of variables, so we don't really do anything with substitution. This is the main thing we're going to use is elimination. When we do this, when we add 2 lines together, so picture these are 2 different lines, we get a third line, right? X equals 3 or 4x equals 12 or whatever you want to think of that as. That's another line that goes through the same place as the first 2, the intersection of the first 2. So when we do that, when we add multiples of rows together, picture that you're getting another, like in 3 dimensions, you'll get another plane that also goes through the same intersection. So when we're doing that, we're getting ourselves another thing that has the same intersection point as the first set of equations. So we will get this other equation that we're then solving. Adding multiples of one equation to another gives us another equation going through the same intersection point. Okay, this produces what we call an upper triangular system. Okay, meaning the non-zero coefficients form a triangle. Okay, so we kind of end up with this triangular shape here, where as I move down the triangle, I'm getting less and less variables. That's going to be our goal here. Obviously, when you do it with Algebra 1, you kind of can eliminate whatever you want, and your less variables may end up on the top equation or the bottom equation or whatever. Here, we're going to try and organize, because again, we're trying to create a system that'll work for 10 variables and 10 equations. So we kind of want an organization, a plan of attack that'll kind of work every time. So we're going to go for this upper triangular system, meaning as I work my way down, I'm eliminating variables. That way at the very bottom, I can solve for 1 variable. Move up, and the next equation has 2. I can use the one I found, find the second. I can move up. There will be 3 variables. I can use the 2 that I've now found to find the third, move up, use the 3 I found to find the fourth, and so on. And basically, no matter how big it gets, from the bottom up, I can start finding variables and then plug those into the next equations. Okay, so we call this upper triangular. That's going to be kind of our goal for most of the stuff that we do. Sometimes elimination fails. It fails usually when there are no solutions. So like if I take these 2 equations and I try and solve the system of equations, I may look and think, I can eliminate the x's by taking -3 times that entire first equation and adding it to the second. Okay, or I could take a third of the second and subtract it from the first, or however you want to do it. If I take 3 times the first and subtract, I'm going to get -3x, and 3x gives me 0. I'll get a 6y, and a -6y also gives me 0. And then I'll get a -3, and 11 gives me 8. Okay, this should trigger a warning in your head that 0 does not equal 8. Something is wrong here. Either you made a mistake and you should go back and look, or something's wrong. This means there's no solutions. There is no x and y that will make both lines true. With these ones, they're parallel. If we graph these 2 lines, they're parallel lines. If you solve them for slope-intercept form, you'd see the same slope. Notice that the coefficients in the first are a multiple of the coefficients in the second. That's how you can kind of recognize parallel lines here. So no solutions. It means elimination won't really be helpful in that case, but that's because there isn't a solution. The other one where elimination is not very helpful is when there are many solutions. Okay, so here's very similar lines. If I take -3 times the first and add it to the second, I'll get 0 plus 0 equals 0. This time, at least, that's true. Okay, 0 is equal to 0. All that's telling me is there are infinitely many solutions. These are the same line. Okay, notice not just the coefficients in the first are a multiple of the second. The entire first line is a multiple of the second, meaning it is the same line. So any x, y that I plug in is on both. Okay, if it's on one, it's on the other. They're all intersection points. So in that case, when we do elimination, you're not going to get something to solve for. You're going to get like 2 equals 2. Yes, that's true. Or something like that, and you won't have a variable to solve for at all. Otherwise, if you don't end up with one of those situations, we can use elimination to find a intersection point, okay? Find the solution to the system of equations. So we again are our goal is to see that this could be useful in larger systems. So if we go up to 3, which most of our examples will be like 2 and 3, but you should be able to picture how this would work in the larger thing. What we're going to be working on is kind of setting up a method that will work in all systems, larger ones as well. So what we'll always try and do first is we're going to try and eliminate these two numbers first. Okay, we want to eliminate both of them first, because if I eliminate, say I just like eliminated this one. And then I move on and I'm like, well, now I want to get rid of this y. There's no multiple of another row I'm going to be able to add to get rid of that y without reintroducing x's, right? I'm going to now have, there's no multiple of this that I could add to like this that could get rid of the y's but not put in x's again. And my whole point is I want to eliminate x's and y's in that bottom one, x's in the second one, and then leave the first one alone. So I'm going to focus first on getting rid of these two x's. That way, once they're gone, I can focus on getting rid of this y by some multiple of the second row, which has no x's in it to put x's back. Okay, so I kind of start on the left column, and I'm going to try and eliminate those x's in the left column on the second row and the third row. So like the second row, I could take row 2, and I could add 2 times row 3, for example. You got multiple options. If you do it correctly, you should end up with the same answer, no matter if you go a different route or not. So I could take row 2 and add 2 times row 3, and that should eliminate those x's. Okay, for that second one, I could take row 3 and add row 1. Right, and that should also eliminate those x's. So after doing that, my first one stays the same. I'll have 2x plus 4y minus 2z equals 2. Okay, and now I'm going to take row 2 plus 2 row 3. So 4x plus 2 times negative 2x is going to give me a 0. And then I'll have 9y plus 2 times negative 3y. So 9 minus 6y is going to be a 3y. Okay, and you don't have to write the 0. I'm just putting it there for right now. And then I'm going to have negative 3z plus 2 times 7z. So negative 3z plus 14z is 11z. And then don't forget to keep doing it. It needs to happen to the whole equation. So I'll also have 8 plus 2 times 10. So 28. Okay, if I do that second one, row 3 plus row 1, I'll have negative 2x plus 2x is 0. I'll have negative 3y and 4y is y. And then 7z and negative 2z gives me a 5z. And then 10 and 2 gives me 12. Okay, now I've gotten rid of the x's. I'm closer to being upper triangular. Upper triangular, my goal is kind of have this thing here. These are my only variables. So I'm getting closer because I've eliminated some of them. At this point, I would start attacking column 2. Okay, if it was a large one, I would attack everything in column 2 towards the bottom. But here, this is the only one I really need to worry about. I want to get rid of the y, and then I would be upper triangular. I don't want to mess with column 1 or 2 anymore. Okay, 2 is already as it should be in an upper triangular system. It's got the 2 variables. So now I just need to go to the third one. I do not want to add a multiple of row 1. If I add a multiple of row 1, I will reintroduce x's into that row and have to then figure out how to get rid of them again. So I've gotten rid of the x's. Don't add any more rows that have x's in them at this point. Okay, so I would take something like 3 times row 3 minus row 2. Again, that's not the only option. There's a lot of times there are other things you could do. I mean, in this case, there's not a lot, but the larger the system gets, there might be multiple options. in the end, you should end up with the same answer as long as you've done it correctly. So I'm going to leave the first and second row alone. And then I'm just going to take 3 times row 3 and subtract row 2. So 3 times y minus a 3y is going to give me 0. And then 15z minus 11z will give me a 4z. And then 36 minus 28 is 8. Okay, and now we've got our upper triangular system here. Those are obviously not the same planes as we originally had. But these planes all intersect in the same place as these planes do, and they intersect in the same place as these planes do. Okay, by this method, you're just getting other sets of planes that have the same intersection point. So it's okay, they're not the same. You have obviously changed the planes that we're looking at, but they intersect in the same spot. And now notice, starting at the bottom, 4z equals 8, so z is 2. Then I could move up to the next row, plug in z equals 2, and I could find y. Then I could move up to the next row, plug in z equals 2 and whatever y would be, and find x. Okay, so that's kind of my goal, is to get into this upper triangular system. And so you could see if this got larger, you'd do the same thing. In the first row, eliminate all the x's under the first row. In the second one, eliminate all the y's under the first 2 rows. In the next one, eliminate all the z's under the first 3 rows. And then you would keep going. If there were more variables, eliminate moving from the left over. Okay, kind of focus on those columns first. Okay, so in terms of matrices, we're going to use matrices because they help us keep the work organized. Again, with a 2x2 system, even a 3x3 system, it's not really any faster. You probably could just solve the system of equations here. When they get larger, it gets very confusing if you're just going to randomly like try to substitute or try to eliminate and just like figure it out. It's going to take a lot more time than having a kind of organized, planned approach. So we're going to use matrices to do that plan. Today, we're not even going to finish. We're just going to kind of practice setting it up. So I'm going to have my coefficient matrix that we did yesterday, that are just the coefficients of the equations, where I'm sure the x's, the y's, and the z's line up in the same column, times x, y, z. Okay, a vector, column vector with an x, a y, and a z in it, should give me a column vector with a 2, an 8, and a 10 in it. Okay, and again, this is what we'll see a lot of. The entire first test is about solving ax equals b. It's in like a month. So that's telling you kind of how long we're going to spend figuring out ways to make this work. This is a, x, and b. And so when we see this is just a shorter way of writing. That's what we're looking for. Matrix A times column vector x equals column vector b. Okay, and so that's how we're almost always going to rewrite our system. We're not going to leave it as separate equations. We're going to rewrite it as one single matrix equation. All right, everything we'll do is basically going to be multiplying matrices to solve the system then. So make sure you know these 3 things about matrix multiplication. 1, we already went over this yesterday. All multiplication is dot products of the row of the first matrix with a column of the second. So any element you basically look at, like element B3, would come from multiplying row 2 of the first matrix with column 3 of the second. Okay, every single element, you're just going across the first one, down the second, and multiply, 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 multiply. Okay, multiplication is associative. It's like when we see we're multiplying matrix A times B times C. I could multiply A times B, then C. Or I could multiply B, then C, and then times A. But it needs to stay in the same order. Okay, it is not commutative. AB is not the same as BC. So in the associative one, this is not the same as multiplying B times C then A. Okay, you can't be like, oh, I'm going to do it that way. If the A is on the left, it needs to stay on the left. Okay, don't start rearranging the matrices. It kind of has to stay in the same order. It's not that they will never be the same. It's just that they are most of the time not the same. It's like the identity. You can multiply that on the same side and they'll be the same. But in general, AB is not the same as BC. So if I'm multiplying in order, you guys are used to in algebra, it doesn't really matter if I multiply on the left or the right, I'm just multiplying. Here it does. So when we're doing matrix multiplication and we're setting these things up, it matters where you put, oops, just realized this is BA. Sorry, AB is not equal to BA, not BC. The order matters. So don't just switch them around. Okay, when we're solving, it's going to matter if I'm multiplying from the left or if I'm multiplying from the right. So when we see like AX equals B, we may think of like the equivalent, well, I could solve for X by dividing by A. Well, we can't really divide by a matrix, but we will have something we can do there. You're going to have to deal with A by multiplying both sides on the left. Okay, you can't do something like, and we will do this later, like I'm going to multiply by the inverse of A to get rid of A. You can't do this. Say, I'll get rid of A. You'd have to put this here. Okay, it's got to be multiplying from the same side. So don't switch things around. Okay, we'll get to that anyway. We're not there yet.
I have a question.
Yeah.
If it's not commutative, like AB is not equal to BA, then why up there is it A?
Oh, sorry.
C? Oh, okay.
Thank you. Yeah, it should not be BCA. Yeah, sorry. Yeah, ABC, you could multiply the AB or the BC first. The A needs to stay where it is. Don't put it at the end. Thank you. Yeah, that should be not equal, not equal. Okay, so again, for the most of the rest of the semester, we will be looking at this thing AX equals B and trying to figure out solutions, trying to figure out what it means, trying to figure out where it's used, all that stuff. Just make sure you're aware. A, we already went over this, but A is the coefficient matrix. Okay, it's going to have a bunch of constants in it that are the coefficients of the variables. Each row are the coefficients of each equation. Each column are the coefficients of each variable. So all the x's, all the y's, all the z's will be in a column with each other in this matrix. X is a column vector, which really is like, it's a column matrix. Okay, we treat it like a vector, but we're going to also treat it like it's one column matrix of our unknowns, essentially of our variables. Okay, x, y, z, x1, x2, x3, a, b, c, whatever it is we're trying to solve for, we put them in this variable, this vector we call x. And then b will also be a column vector of scalars. Okay, basically when we have our system of equations, b will be all the stuff that doesn't have a variable in it that we move to the other side of the equation. Something x plus something y plus something z equals something. It's that stuff on the other side of the equation from all the x's, y's, and z's. That's what we're putting into b, are the scalars that we're kind of setting our equations equal to there. All right, so we're going to look at two different operations that we're going to use with matrices. One is elimination. We're going to still do elimination. We're going to do it as matrix multiplication. Okay, and the goal here is we can actually do multiple eliminations at once by matrix multiplication, as opposed to kind of having to do a bunch of different separate things. We could do one matrix multiplication and it can do multiple eliminations at once. Okay, we're not going to do that today. We're going to do it one at a time. We're going to go fairly slow. So what we're going to look at is trying to just take this simple column and subtract 2 times the first row from the second. So what we're looking at is how would we get via multiplication. So we're going to do some matrix times b. That's going to cause us to get b prime. B prime just indicating we've changed it. where we've subtracted 2 times the first row from the second. So we have 2, 8 minus 2 times 2 is 4, and 10. Okay, a simple elimination. So we're going to start really simple here. Is we're going to look for a matrix that will cause that to happen. And that matrix will cause it to happen to anything we multiply it by. Okay, where it's an elimination matrix, meaning I'm going to take that matrix and if I multiply, it will cause row 2 minus 2 times row 1 of anything I multiply it by. Okay, so to do that, we're going to start with the identity. We should already know when I multiply by the identity, nothing changes. If I took that b and I multiplied by the identity, I would just get b again. But if I start to change things in b, and you could do this just via experimentation, like change a number, pick a 0 and change to something else, multiply and see what would happen. But what we would see is I would want to change what's in the 2, 1 spot. Okay, second row, first column. If I change that to a number, it'll take that number times this column, this row, sorry, times 1, row 1, and add it to row 2 of whatever I do. So I'm going to change, I really probably should have that as a lowercase letter. What's in the little 2, 1 spot, that's going to mess with row 1 and row 2 of what I multiplied by. Okay, which is what I'm trying to get here, is to add a multiple of row 1 to row 2. I'm going to change what's in row 2, column 1, and that's going to cause that to happen. Okay, so if I put a negative 2 in that spot and multiply by b, it'll give me 2 times the first row subtracted from the second. From the left, okay, it doesn't say here, everything we do here is going to be multiplying from the left. So b was 2, 8, 10. If I take the identity matrix, and all I do is I put a negative 2 here. When I multiply, I'll have 2 times 1, 0 times 8, 0 times 10 is 2. I'll have negative 2 times 2, 1 times 8, 0 times 10 is 4. 0 times 2, 0 times 8, and 1 times 10 is 10. Okay, notice it causes the change to occur that we're looking for. Okay, so basically in that little A21 spot, it'll take a multiple of this, and it will subtract it from this one. So it'll take row 2 minus a multiple of row 1, whatever multiple you put in there. Since we're trying to get like upper triangular, we're really only gonna ever look at kind of this group. That's what we're trying to eliminate, is that lower area. So that's really all we're ever going to be looking at in these elimination matrices. So what we're going to try and get comfortable with is trying to come up with ones that would do what we're looking for them to do. So an elimination matrix to add 5 times the second row to the third. So we just said A21 will do a multiple of row 1 minus, subtracted from row 2. Okay, that's what the A21 would do. It would take a multiple of row 1 from row 2. So I'm trying to look at what element would I change to take a multiple of the second row and add it to the third. So I would want to look at the element that's in the third row, second column. Right, that'll take a multiple of row 2, subtract, and I keep saying subtracted, you could add too just by changing the sign, from row 3, which is what we're looking to do. Yeah, so that's what I'm saying. You could change this to add just by changing the sign. So we call that, and I didn't say that up here, we call this elimination matrix E21. Just saying it's the elimination matrix that will affect rows 1 and 2. We'll call this one E32. And it's taking the identity matrix. And all we do is change what's in row 3, column 2. Subtracting, you would put in a negative number. Adding, you'd put in a positive. So we just put in a positive 5 there. And so notice if we did E32 times B, what was B2, 810? If we multiply, we'll get 2 times 1, 0 times 8, 0 times 10 is 2. 0 times 2, 1 times 8, 0 times 10 is 8. 0 times 2, 5 times 8 is 40, plus 1 times 10 is 50. And so it will have taken 5 times row 2 and added it, in this case, to row 3, which is what we were looking for. All I do to subtract is I just change the sign. Okay, so if we generalize this, when we're looking for an elimination matrix that subtracts a multiple of row j from I, we change what's in the ij position. So if I want to, and again, this you could do adding just by changing the sign. Here in the little generalized formula, we use a negative k and we subtract. But if you do a positive number there, it's going to add. So if I want to subtract a multiple of row j from row I change what's in the ij position. And again, we're really only going to use these down here. Because my elimination, I want to kind of eliminate that stuff to get the upper triangular. So those are the things I'm going to do is do things like add a multiple of row 1 to 2 to get rid of this number. Add multiples of row 1 to 3 to get rid of this number. Add multiples of row 2 to row 3 and get rid of this number. Okay, just to get to that upper triangular, we're really going to only look at that bottom part there. So this would be the E31. For our 3 by 3s, we always have E21, 31, and 32. As they get larger, you would have, ones down here as well. So you kind of want to get to the point where you're not actually multiplying because these are really simple to do, but where you can kind of look at it and know what does this thing do. Okay, again, always you're multiplying from the left. So if you put this over here, it's not, well, one, you're not even going to be able to multiply. It doesn't work that way. But in general, even if you could, you won't get the results you think you're going to get. It has to be on the left. So when we're multiplying on the left-hand side here to cause this change to happen. And so even without sitting there and like multiplying, you should be able to tell row 1 and row 2 aren't going to be unchanged. And all it's going to do is take a multiple of row 1 subtracted, or negative 4 added, or 4 subtracted, however you want to think of that. It's going to take negative 4 times 1 and add it to 9 is 5. So you kind of want to see this and understand it's going to cause this elimination and not really have to multiply to see it, but just be able to go, oh, this is an elimination matrix. This is what's going to happen. Okay, our goal here is going to be that I could string these things together. Multiply by a matrix, and it's going to cause all of them to happen at once. It looks like 4 different operations, but literally multiply these together in that order, and it's going to cause those things to happen in that order. Okay, this you can multiply to get one matrix that causes all 3 eliminations at once. Multiply by something, and it will do this, this, and this all at one time. Okay, be careful because as we do that, we're not doing it yet. As we do that, what's happening is this is first. Okay, that's the thing being multiplied by a first. Don't read left to right on these. Since we can't change the order of multiplication, this is what's going to get the change that's going to occur first. Then it's going to be this one, because that's what's now being multiplied. then it's going to be this one. So the order is going to matter, and it's really going to be the thing on the right that's going to happen first. So if I do that, it's different than if I did like, okay, this one's going to happen first, then this one, then this one. And they're obviously each change that occurs affects the other one. So just as we get there, just keep making sure you remember you can't just move things around. Once I've set those in an order, that's what's going to happen in that order. Okay, so that's where we're getting to. The homework for now is pretty simple, just like come up with these things, use these things one at a time. Okay, so the last thing we're going to end with is row exchanges. These ones are a lot easier. This will exchange two rows when you multiply, again, from the left. So say my equations or my like coefficient matrix, when I lay it out, it's 0, 0, 4, 1, 2, 3, 1, 1, 1. And I'm like, well, boy, that first row would make a really good fourth row because it's already got two spots eliminated. So if I want to switch these two, I would multiply by what we're calling P13. It's a permutation matrix. That's why it's called P. It's just going to switch row 1, row 2. So I'd multiply on this side. And that'll just cause those to switch. So now two of the eliminations I need to do are already done because I've got a 0 and a 0 in those first two spots. So if I take 0, 0, 1, 0, 1, 0, 1, 0, 0, and I multiply by 0, 0, 4, 1, 2, 3, 1, 1, 1. Notice that I'm going to get 0 times 0, 0 times 1, 1 times 1. 0 times 0, 0 times 2, 1 times 1. 0 times 4, 0 times 3, 1 times 1. And then I'm going to get 0, 1, 0, 0, 2, 0, 0, 3, 0. And then I'm going to get 0, 0, 0, 0, 0, 0, 4, 0, 0. So I'm going to get the exact same matrix where it's just switched rows. And now notice I'm almost upper triangular already. I don't have to go through eliminating those first two spots. So permutations are nice, row exchanges are nice. If you notice that some of my equations already have some of the variables gone, I may want to put them in one place to kind of get it closer to upper triangular to save me some other computations there. So all you do is you take the identity, switch the rows of the identity that you want to cause the switch rows 1 and row 2 of the identity. When I multiply, that'll switch rows 1 and row 2 of whatever I'm trying to do. Okay, switch row 1 and 2 of the identity, then 2 and 3. It's going to cause those same two switches to occur. And we'll go more over row exchanges later. But that's how kind of you do that. Okay, the augmented matrix is what we'll be seeing this whole time. So we're looking at this AX equals B. And just remember, everything we do to the left side of the equation, we want to do to the right as well. Just like in Algebra 1, you would not want to mess with the left side of the equation and leave the right side alone. So the augmented matrix just puts our coefficient matrix in the same matrix with the right-hand side of the equation. Okay, I usually put a dotted line. Not all textbooks will do that. It creates one matrix. Now, whatever I do to this matrix, it'll cause the change on both sides of the equation. So like if I do an elimination on this side and I multiply, it'll do the elimination not just to the coefficients, but also to the right-hand side of the equation, which is what we'd want to do. If we started adding rows, we want to add the entire thing, not just the coefficients. So if I did an elimination here, it doesn't really matter that I've added a column. Your elimination matrix would have been 3 by 3. This is 3 by 4. We can still do it. And you'll get a new 3 by 4 where I've got the change to the row that I'm looking for. You obviously cannot add rows. And then you'd have to redo your elimination matrix because your elimination matrix can only be multiplied by something with 3 rows in this case. Okay, but our augmented matrix is just putting the two things together. It's treated as one 3 by 4 matrix, just remembering that that last column is your scalars, not coefficients there. So again, kind of where we're heading is I can kind of make these things all happen at once. I could take I could do an elimination, a permutation, an elimination, an elimination, an elimination. If I put these all together into one matrix, it'll do this, 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 and this all in one multiplication. Okay, all in one step, as opposed to sitting there and doing each step at one time. Is we're heading towards kind of being able to put these things together into a matrix, multiply them all together, and I get this one matrix that'll cause a bunch of changes in one step, as opposed to individual steps one at a time, which again is great for like computer computations or whatever. If you're doing this on a computer or doing a computer program, it's a lot less steps to have in there. So that's kind of where we're heading. For right now, your problem set will be like, what does this elimination matrix do? Come up with one that'll do this. And it might ask you to start thinking about what would happen if I wanted to do this, then this. What would I multiply A by to get this to happen, then this to happen? Just remember, order matters, okay, when you're doing that. All right, tomorrow we're doing a MATLAB. So again, it'll basically be an independent day to work on the MATLAB. If you need help on it, I'll be available, but otherwise you guys will work on that. Problem set is due next week at the end of the week. So make sure you are starting to look at that. And then if you guys need anything, let me know. Otherwise, y'all have a good rest of your day and I will see you guys tomorrow.
Thank you.
Thank you.
Thank you.
Thank you. Have a nice day.
Thank you.
Mr. Smith, I have a question on the elimination matrix. Is the subscript like the spot that changes?
Yes.
Okay. And
Yeah.
then also for linear combinations of planes, I'm confused what the final matrix should be.
With linear combinations for planes, it should be something times a vector plus something times a vector,
Mhm.
possibly plus another vector, but no matrix really. So what you're looking for is basically two vectors parallel to the plane, as long as this one only happens if the plane is not equal to 0. So if you have like
Right.
ax plus by plus cz equals 0, you only need two vectors. And you basically are just going to come up with two vectors that are parallel to the plane.
Mhm.
And then any linear combinations of those will describe all the vectors parallel to the plane.
Really? So if I like switch up the two vectors and like A is X and B is Y.
I should not use those letters because those are not, that's not this A, B, and C. This is other multiples. It doesn't have to be those specific multiples. So like yesterday, I basically said I would solve for 1 so that I could start plugging stuff in here, get one vector, plug something else in here, get another vector. And then any two multiples of those vectors will describe all the vectors parallel to the plane. So it's kind of like how our equation of a plane describes all the points on the plane. This will describe all the vectors parallel to the plane.
Okay. But for like the D and E, it was X and Y.
Yeah, because the way it technically can be, you can use other letters. The way I did it, so like say I have, well, I'll do it a different one than I did yesterday. So like,
Mhm.
say I solved it and I had this. So the way I would make sure I was coming up with independent vectors is I would just let x be 0, y be, or sorry, x be 1, y be 0. I mean, not y, z be 0, sorry. These variables, I just start plugging stuff in. So if x was 1, z was 0, y is 2. And so I'd have the vector 1, 2, 0. And then if I let x be 0 and z be 1, I'd have y as 3. And so I'd have this other vector 0, 3, 1. Those are two vectors parallel to the plane. The plane goes through the origin. And basically, since I have this point on the plane, I could think of that as going, this vector goes from the origin to that point. The plane goes through from the origin to that point as well. So like this is a vector in the plane, essentially. Same thing here. Since the plane goes through the origin and it's got this point on it, I could think of this vector that goes from the origin to that point, and that vector would be 0, 3, 1. right? So basically
Yeah.
what I've gotten is plane, if that's the origin, I've got a vector going like that.
Mm-hmm.
If I take any combination of those, any linear combination of those, I'll get other vectors in the plane. Kind of like when I take multiples of I and j.
Oh,
So here, the reason I use x and y as my, or sorry, well, here I'd use x and z as my multiples was because x was 1. So really any multiple of that I plug in, you'll get the something that works. But really you could think of this even as any multiple. It doesn't have to be x and z specifically. I chose those because x was 1 and z was 1, and it gives you the equation. If you were to add these together, I'll get a 2a plus 3b and b.
mm-hmm.
I used x and z because I wanted you to notice that those were the same thing.
Oh, okay.
That y equals that, and this is like x, y, and z. So I kind of wanted to see whatever x is, whatever z is, y will be 2 times x and 3 times the b that you choose, or the z that you choose.
Okay.
But it
So-
really can be any multiple. It doesn't have to be x's and z's or x's and y's or whatever. We're just saying every multiple you take of these two vectors, every linear combination, that'll create other vectors in this plane.
Okay.
It'll never create one that's like bouncing off the plane, like poking out. They'll all be in that same plane.
Mm-hmm. Okay. So can you just write A and B? Like
Yeah.
if you had,
That's fine.
yeah.
Yeah.
Oh, okay.
And you could even, there are infinitely many choices of vectors you could choose. The only thing you would want to make sure is that you don't do something like A times 1, 1, 1 plus B times 2, 2, 2. You need two different, like,
Yeah.
kind of like two to make all the other ones. You don't want two multiples because these are essentially the same thing since we're taking multiples. You want to make sure you're choosing them to be independent of each other, independent meaning not parallel. So that's kind of why I do this, is I know if I make x1 and z0 and x0 and z1, they will not be multiples of each other because no multiple of 0 is going to give me 1, and then the same multiple of 1 going to give me 0. Right? That's kind of how I ensure they're independent. But you technically could plug in x equals 1, z equals 3, and x equals 3, z equals 1, and get a different set of vectors. Multiples of those will still describe it, the plane too.
Okay. So you only need like this describes all the things parallel.
Yeah, so like if I came up with just some other random vector in the plane, you could figure out some multiple of 1, 2, 0 and some multiple of 0, 3, 1 that would give you that vector too. So like I usually like to think of this as the standard unit vectors, like we have I and j. Every vector that I draw in the xy plane is some multiple of I plus some multiple of j. Every vector in this plane is some multiple of 1, 2, 0 and some multiple of 0, 3, 1 added together.
Okay.
Does that kind of make sense? It's
Yeah.
like using an x-axis and a y-axis for the plane, only they're not always going to be perpendicular and not always one unit. But you're just trying to choose these two vectors. I can add multiples of them together to get all the other vectors kind of in the plane.
Okay. That makes sense. Thank you.
Huh.
Could you just briefly review again, like how you do the matrix multiplication to like a 3x3 matrix? Like I think there's one in the examples. If you don't want to draw one out. Oh,
That's fine.
I was pretty sure I remembered it, but I wanted to make sure I was just doing it right because I got the correct numbers. But I was wondering if there was maybe just I don't know. I just want to make sure I was doing it right.
So like each element, you're going to take like row 1 times column 1.
Mm.
That'll give you this first element. So I'd have 1 times 1, 2 times -1, and 3 times 3. So it's 9 plus 10 minus 2 is 8.
Mm-hmm.
And then for this next element here, I would stay in row 1, but then I'd multiply by column 2.
Mm-hmm.
I'd have 1 times 2, 2 times -1, which is 0, and then 3 times 4 is 12.
Okay, so like the position that you're in and the resulting like matrix, it just like the position that it is tells you exactly what you need to multiply.
Yeah, so if I'm in position 1, 2,
Mhm.
that's row 1 times column.
Column 2. Yeah. Okay, that's what I thought. I just wanted to make sure I was doing it right.
Yep.
All right. Thank you so much.
Uh-huh.
Have a good day.
You too.